I'm going to be talking today about initial experiments with Decaborane in a dense plasma focus. And I'm representing the work of our research team, which in addition to myself consists of Dr. Saeed Hassan, our research experimental scientist, Heidi Karamitsos, who's our CIO responsible for our software and many other responsibilities, including director of communication, and Rudy Frisch, our mechanical engineer. So the dense plasma focus, even though it's existed for 60 years, is now familiar to everyone. So I'm just going to review briefly how it operates and what the goal our overall program is. So we are into commercial fusion. We're a private company, and our goal is to research and develop a 5 megawatt fusion generator, safe, no radioactive waste, compact, cheap, and decentralized, using hydrogen-boron fuel. So we're using the dense plasma focus device, which works by exploiting rather than fighting the natural instabilities of all plasmas. So we use the pinch effect, the attraction between electric currents moving in the same direction, to form a series of guided instabilities that increase the temperature and density of the plasma, as in this animation. So we first dump electricity from a capacitor bank into a vacuum chamber across the outer electrode, which is the cathode, and the inner electrode, which is the anode. And this causes the first instability, which is the formation of these filaments. So the filaments run down to the end and converge into a single filament, which kinks up through the kinking stability into this remarkable plasmoid, which is a self-contained transient lump of plasma, which is contained by its own magnetic fields. Through viscous heating, that heats up to as much as 260 keV, temperatures of interest to proton-boron fusion. So that's the general device that we're using. FF2B is our fusion experimental device in Middlesex, New Jersey, with a beryllium cathode, which is 5 centimeters in radius, and a beryllium anode, 2.8 centimeters in radius. So a very compact device. And our entire vacuum chamber is only 2 meters tall, and that contains the entire experiment, surrounded by a capacitor bank, which is 60 kilojoules, 40 kilovolts, with a peak current of 1.6 megaamps and a peak power of 60 gigawatts. For comparison, that's the approximate electric generating capacity of the country of Poland. Of course, we only generate that power for a microsecond. So the outline of what I'm going to present here today is, first, we've done experiments with deuterium and it confirmed theoretical predictions that we use for our expectations that we can reach net energy with hydrogen-boron. Second, I'm going to present our exciting initial results with Decaborane, what problems we've encountered, some of the solutions, and finally the next steps for the future of the experimental antennae. Now, our theory is based on this process of filamentation, but previous to past year, our filaments were disappearing, were disrupted during the rundown. Now, this GIF shows a series of ICCD images taken at different shots with the same conditions. So it makes a little movie, and it shows that filaments that are well-defined at 600 nanoseconds become completely disrupted at 1200 nanoseconds. before the end of the rundown, which is 15 to 1600 nanoseconds. So that's what we were doing. But due to the various improvements that I will discuss, we now have filaments that survive until the compression phase, that phase that we saw in the animation, where it contracts into the plasmoid. So this is now what we see with deuterium at 1,000 nanoseconds, where we have well-defined filaments, 4 filaments merging into 2 filaments, and still at 1,400 nanoseconds, right at the end of the rundown, we still have the 2 helical filaments. I hope people can see this. We can't block the sun, unfortunately. Can people see that aura? Okay. So that's the first achievement that confirms our basic theory. Now, the theory also predicts for each gas an optimal Guanidan velocity for the formation of filaments and the formation of the plasmoid. And this is a very simple result, simply the atomic mass and the atomic charge of a gas. So an unequivocal prediction. And we took shots with deuterium in which we translated that prediction into a rundown time. So knowing the 6.6 centimeter free length of our anode, we can convert the optimal velocity into an optimal rundown time, which is this red line, 1,600 nanoseconds. And what we see when we plot the fusion yield in millijoules against this, we first see, as the time gets longer, a rise to the optimal, which is exactly at the predicted time or velocity, and then a rather sharp drop in yield by approximately a factor of 3 as we go into this too slow rundown, too long rundown times. So again, confirmation of the quantitative theory. Our videos come out of LPPFusion's research in fusion energy, the energy which will power a future of abundance for all, with a sustainable economy in a clean environment. Goods, housing, and transportation will be affordable to all once fusion kicks in. Fusion energy is the key to building a better world now. Support fusion research, $10 a month at lppfusion.com/support. The link is in the description. Thanks. And finally, and perhaps most important, you have preliminary confirmation of the fusion yield scaling with current. Now, with smaller DPFs, below approximately 0.8 megamps, people observed decades ago a scaling of approximately current to the 4th power. So that was a very good optimistic scaling. But then we all ran into this plateau in which the fusion yield did not increase at all from about 0.8 megamps up to about 1.6 milliamps. We had a theoretical explanation for that based on the current filaments being too small in current to contain the maximally compressed plasma. So what we're seeing here is that we have a tentative breakthrough to the theoretical scaling line. This again is not a fib, this is a theoretical line of I to the 9th power, taking into account the current of the individual filaments. And we're breaking out this plateau at just about 1.6 mediums. Now that is approximately the limit of the device as it's currently configured, but we are capable of moving the device up considerably to about 2.4 milliamps. So in doing this, we got a new record yield of 0.26 joules. Coincidentally, just what our colleagues just announced for PB11. And we are also very pleased to have only 25% yield variation with the same conditions. So that's pretty good for this device, which has been notorious for big yield variations. These we achieved plasma parameters 3 times 10 to the 19th per centimeter cube. Note the units, this is about 1 million times of what you have in a total. We measured by time of flight 70 keV ion temperatures and a confinement time of these little plasmoids of about 60 nanoseconds. Now earlier we got with tungsten an even higher temperature because the viscous heating is actually encouraged by the tungsten impurities. We expect to regain such high temperatures with boron because, again, the large amounts of boron with the 5 charges will again encourage viscous heating. The goals that we seek with the Decaborane experiments are much higher density, somewhat higher temperature, and actually we will only need shorter confinement times for these tinier plasmoids that will only be of the order of 10 to 20 microns in radius. Now we achieved all these results by a series of improvements over the last 2 years. We increased the current of the present configuration by using 2 switches per capacitor, reducing the inductance of the switches, magnetic energy stored in them. We reconfigured the cathodes so we would get half the number of filaments and thus double the current per filament. We developed a cleaning shot, a mix of deuterium and nitrogen, which I'll come into a little bit more later. And we increased the free ionization current. Free ionization current is a tiny DC current that precedes the main shot and smooths the ionization levels to create a more symmetrical main shot. Doing all this, we were able to get 13% of our capacitor bank energy into the plasma. So one of the big advantages of DPF is since the energy starts out as electricity and remains electricity, we can get very high efficiencies compared with, for example, lasers. So then we made a big step of finally starting our long-plane Decaborane shots in November of last year. So Decaborane, or some people call it boron hydride, is B10H14. It's a solid at room temperature, and therefore heating is required for vapor generation, which allows us to control the amount of vapor very precisely. But initially we had heating problems. We had to heat the entire device so that no part of it was less than 75 centigrade because the Decaborane would condense on those cooler parts. And that would allow a fill pressure of at least 2 torr, which is what we expect we will need for the initial experiments. Well, how hard can that be? You know, how many plasma physicists does it take to boil hot water? But it turns out that it was difficult because the main insulation between our top plate and our bottom plate, the hot plate at 40 kilovolts, is mylar, and we didn't want the mylar to go above 100 C. So keeping the mylar cool at below 100 C and everything else warm at 75 C took us all the way to June. So June, we developed a comprehensive insulation. You see the insulation going on here, being installed. First, aluminum foil to spread the heat, and several layers of fiberglass insulation. We optimized the thermocouple's placement so we would actually be getting the heat from the heating coils, the heating tape, in the right spots and not too much. And finally, we found that our gauges became inaccurate at these modest temperatures, so we bought heater gauges that maintain their own temperature at a constant, so we could rely on them. And this is the Decaborane, normally it would be invisible inside its insulated sample chamber, but here it is being converted from the liquid state to the gaseous state. Now, during the same year where we were solving the heating problem, we encountered another problem, which is that we were not getting a pinch. Now, a pinch is the time at which the plasma forms, where the plasma pitches together. And one of the many signs that you get a pinch is a sharp increase in the voltage on the anode, as measured by our high voltage probe. So in the typical early shots, like this one in February, with a mix of 1.5 Decaborane and 2.5 torr deuterium, you see that there's a smooth decline in the voltage and no pinch at all. So we've been able, by June, to actually solve this, and we were getting significant pinches with a heavier mix of deuterium. So this is mostly deuterium by number, 22 torr deuterium and only 0.75 torr Decaborane. And after deuterium nitrogen cleaning shots, these cleaning shots basically clean off the small particle debris from the previous shot. This debris is formed, even the pure deuterium, from the beryllium anode, but it's much worse with the boron mix. So it has to be cleaned off. With these cleaning shots, we got from the deuterium a significant neutron yield, or 6 times 10 to the 9th. Now, we may have gotten some hydrogen-boron fusion, but it would have been too small to measure, so we're not claiming that result. Now, to be sure that we were getting these results by the cleaning shots, we did some deuterium shots with and without cleaning. So this is a deuterium shot immediately after a Decaborane shot. And you see a very small pinch and a yield of only 5 times 10 to the 9th, which is small for pure deuterium. But when we simply had the deuterium nitrogen cleaning shot, and then the very next shot after that, the height of the pinch shoots up to 50 kilovolts from 10 kilovolts, and we get 1.4 times 10 to the 11th neutrons. So people were talking about orders of magnitude increase in yield. So just with proper clean, we got 25 times more fusion yield. This is the deuterium. So we're quite confident that that's improving our results with Decaborane as well. Now, the problem that we're currently working on is that during the rundown, the hydrogen or deuterium, whatever mix that we're adding, and the boron ions don't state yet. Saying I mean why we quite confident that's happening. So the process that we see happening is basically that there's a speed limit that affects the boron ions, but not the hydrogen or deuterium. So the boron ions are like well-behaved motorists, while the deuterium or hydrogen are like politicians who succeed, the speed limit. So what we actually inspected this from the alpha and critical velocity process. Now, this process has been well confirmed over the decades, both in the laboratory and by spacecraft, which is when you have a velocity, a critical velocity, Vc, so that the kinetic energy of a given ion, and that's the mass of the ion, is equal to the ionization energy of a given ionization state. And the velocity of the sheath does not increase further until all the ions are ionized to back level. So again, another analogy is like boiling water. Until you boil all water away, all the energy goes into breaking up the the attraction of the boron molecules. So this means that the boron ions cannot exceed these critical velocities, but the hydrogen and deuterium ions that no longer have any electrons to get up can exceed these velocities. So there's a conflict with the optimal rundown velocity of deuterium. That's 8.2 centimeters per microsecond. So with a boron ionization 2 and an energy of 25 eV, we get a critical velocity of only 2 centimeters per microsecond, a little bit more, 2.6 centimeters per microsecond for the third level. So this is encountered between 0.4 and 0.5 microseconds into the rundown. And then the big step is the fourth ionization state, tightly bound electron with 250 eV, and that has a critical velocity, 6.7 centimeters per microsecond at 1.3 microseconds into the pulse. So that's really the ultimate limit, because the rundown sheet does not have enough energy to ionize all of the boron ions to this fourth ionization level. So they're left behind. During the compression phase, we have plenty of energy because the magnetic field is rising rapidly and we're compressing less and less glass. But the rundown phase, we get this separation phenomenon. And the evidence for separation is, first of all, we get a strong deviation in both the higher voltage probes and the current traces. So when we look at the current or voltage against time, it diverges at exactly the time that we expect, half a microsecond initially, and then between 1.1 and 1.3 microseconds. The bigger evidence is that the separation that leaves behind the boron ions with relatively little energy leads to structured deposits of the compound of beryllium and boron, which is beryllium boron. So we get these very well-ordered stripes on the anode, as seen in these ambient light images. So the deposition starts about 2/3 of the way down the anode. So you can see at the top of the anode, it's still gray color. In the bottom, it's pinkish. And I hope you can see this before sunlight. So that again indicates the deposition is starting only when this velocity is starting to be exceeded. So what we see close up is 150 micron mini filaments, much smaller than the overall vortex filaments I was showing you, that are formed by a hydrodynamic process in which a fluid is moving past a substance that it cannot entrain. So hydrodynamically, this, for example, is what causes linear striations of water and rock over thousands of years. In our case, it forms these striations that you can see in this close-up are about 150 micron spacing. And the current has to cut through the beryllium boride, which is not a good conductor, to get through the high conductivity beryllium. And one of the unfortunate things about this coating is that it funnels the current into these very narrow grooves. So what happens is the current gets concentrated, and unfortunately on a shot in August 14, it got sufficiently concentrated that it initiated a crack to crack the anode. So you can see that we identified the initiation point of the crack right here. You can see sort of explosion marks going outward. This is blue, not red in color, because this layer is so thin. That's interference color, not the natural color of beryllium boron. So the concentration of the current led to the thermal cracking of the anode. We tried quite a bit before this shot to remove the beryllium boride. It's really too tightly bound, and it's very tough material. In fact, it's being considered as a military armament material, among other useful applications. So we absolutely have to avoid the deposition of this material. We can clean it all subsequently. However, on the last shot, we actually made two advances. First of all, we were running, in order to obtain measurable fusion, we went back to running with a heavy Decaborane mix. So we were running with 1.3 torr of Decaborane and only 2 torr of deuterium, which means that the great majority of the mass is in the form of boron. And we did get a tiny pinch. So this is a definite pinch over here, but it's only 2 kilovolts, so it's quite small. And again, we didn't get measurable fusion, but it does show that pinch is possible with the almost pure Decaborane. So that was exciting. And the last shot got our first image of the filaments forming. This is early in the shot at 500 nanoseconds, but you had quite a good formation, an even formation of the filaments. So that's again a good sign for our future work. Okay, so I'll finish up quickly with our next step. As I said, our first goal is still to get measurable fusion yield from pure Decaborane. We think that measurable fusion will be attained with about half a joule of fusion yield. So that's twice what was recently reported with the laser in China. We are going to install a new anode. Fortunately, we have a spare, and we expect it to be baked out. We have to get rid of the moisture on ML by about November 1st. So we hope to get back to firing about that time. To prevent the separation and the deposition, we simply have to obey the speed law. So by adding a higher pressure to Decaborane, we should be able to reduce the rundown velocity below this critical velocity of approximately 6 centimeters per microsecond. It's not totally straightforward how much you'll need because dust and the shape of the current sheet and how efficiently the boron ions are linked to the magnetic field. But we expect to do this during the rest of this year. And it almost seems a shame to get rid of these beryllium boron deposits. They're rather attractive, even artistic. So maybe we'll sell parts of the old anode as MTFs or something. Who knows? We need to raise money somehow. In addition, beyond this, you want to optimize the functioning of the machine for the second goal, which is 100 joules of fusion yield. We expect that we can get that by optimizing the rundown velocity within the range that we expected. By optimizing the cleaning mix. We know the cleaning mix works, but we haven't optimized which is the best cleaning mixture. And we're going to introduce the axial field coil, which will control the amount of spin in the plasmoid. Too much spin and the plasmoid won't contract fully. Too little spin and it won't begin into the next plasmoid shape. Altogether, we expect about a factor of 4 from each of these factors from optimizing preionization to get us up to 100 joules. And finally, we're going to upgrade to 12 capacitors. These are already on the machine, but only 8 capacitors in use. We'll get up to 2.4 megamps. And due to the very steep scaling law that we anticipate and we've demonstrated with deuterium, we hope with that configuration, we'll get net energy out of the device. So I want to thank LPPFusion's funders, the ABLE Foundation, our many investors and donors. At the moment we're up to about 2,000, and of course, pro bono organizers of this and other conferences. And thanks for your attention.
Thank you very much for the talk, Eric. I would like to open the floor for the questions.
Thank you. Very interesting presentation. I would like to perhaps ask you to say more about the acceleration mechanism when you form this plasmoid. Presumably you have these magnetic field structure that is dynamically changing, okay? And you have figured out a way to turn it into a plasmoid. But all this change is happening in a pre-filled gas or plasma, right? And as you form the plasmoid, how are the energy given to what you later measure to be energetic ions, right? That's actually the first question, but if you could explain that, then I have a different, related to that, some other question.
All right. Okay. It is a bit of a complex process, but it has been studied quite a bit over the 6 decades since the invention in the United States and simultaneously in the Soviet Union of the TPF. Now, I don't have a slide to illustrate this, I'm sure, sorry, but as the radial convergence goes forward, what happens is you have pairs of counter-rotating filaments. So by conservation of angular momentum, these filaments form in counter-rotating pairs. When they start to converge, the filaments start to merge, their magnetic fields are reorganized, and that sudden change in the magnetic field creates strong electric potentials that basically concentrate the energy into the plasmoid. And what you see in the ICCD images is the filamentary structure, which looks like spokes of a bicycle wheel, disappearing, and the plasmoid becoming more and more intense. If you're looking down the bow, which we don't have the capability to do, but my mentors, Winston Bostick and Victoria Nardit, did these series of experiments at Stevens Institute back in the 70s, and they got these very nice down the barrel images. So that's the compression phase. If we look at it from the side, again, I'm sorry I don't get the images right, you basically see the core of this plasmoid that looks like an apple core. So that's formed by this kinking process. Now the kinking process is theoretical. The process, the time that it takes to go from the unkinked to the plasmoid state is of the order of a nanosecond. So that's not really resolvable even with our half nanosecond exposure times. So I've never seen anybody who says that they've observed the formation process. But basically you go from these disappearing spokes to the apple core, and then the center of the apple core, but only in the center, the synchrotron radiation frequency, gyro frequency, exceeds the plasma frequency. So that means that radiation can escape and the B field suddenly drops. That accelerates a beam of electrons in one direction and a beam of ions in the other direction. And this is a repetitive oscillatory process. And this eventually drains all the energy and most of the matter out of the plasma. This is the lifetime of plasma. I started studying this as an analogy to quasars, Herbie-Harrow objects that form at the beginning of the lifetime of a star, and these astrophysical processes. So at all scales have these processes that basically end up converting most of the energy into these concentrated beams. Now the question is, how does that become thermalized? How do you get these high thermal energies? And basically, people studying not this, but seed pinches, which are closely related device, hypothesized that this was viscous heating, basically the conversion of ordered into wave-like and then disordered motion. And we did, theoretical analysis that indicated that we could explain our temperatures with this viscous heating. So that's basically the story in summary.
So I have one next question. I don't need the microphone. I'll be keeping question. The next question is, what is the maximum colloidal flux or the contained magnetic flux in the plasma? Do you have
Okay, not a flux, but we have estimates of the magnetic field. The magnetic field in our experiments has reached about 40 megaGauss. So that would be about 4 kilotesla. Now we don't have direct measurements, but we hope to obtain direct measurements in the coming series, because as the magnetic field goes up, so does the gyro frequency, and it will shortly move into the optical range. So we expect to see, in addition to line radiation, which of course, like everybody else, we get line radiation, we should see a big hump, which represents the gyro frequency and being cut off by the plasma frequency. So then we get a direct measurement from the gyro frequency of the Manson field strip.
So the orbits initially were confined orbits.
Yes, these are completely confined, and we have a lot of evidence of the confinement. And this is not produced by the beam moving vertically, because we carefully measure the anisotropy of the neutrons, and the neutrons are very spherically isotropal. So we've actually calculated and published that the majority of these must be contained. Now, people use this word thermonuclear to not indicate thermonuclear reactions, which is the actual meaning of the term, but to indicate thermal or Maxwellian velocity distribution. And we all know that these plasmas are non-thermalized, and there's no particular reason why they should be thermalized. But we can measure by time of flight the mean energy, and we can measure also the distribution of those energies, which is not that far from Maxwellian. And the mean energies that are confined within this plasmoid go up as high as 260 keV, which we've claimed in the literature is a record for any confined plasma of any device.
So the confinement time you mentioned in your slide, do they refer to the survival time of the configuration?
That's how long the plasmoid lasts. So there's time for maybe several dozen revolutions at the moment, and at net energy there would be several thousand revolutions.
Very well, thank you.
Our videos come out of LPPFusion's research in fusion energy, which will power a future with abundance for all, with a clean, sustainable economy and environment. Goods, housing, and infrastructure would be extremely affordable once fusion kicks in. Fusion energy is the key to an advanced future. Support fusion research. The link's in the description. And thanks.
From both specialists, I understood that from a cathodic mass impact today and from other theories, in order to get proton-boron fusion, you need to be out of equilibrium and to have a hot IO convergence. So, in your device, where is this pseudothermal convergence?
We don't have any evidence for a cold component of the ions. As far as we can see, all the ions are hot. They are actually close to a Maxwellian distribution, even though they didn't have time to get there by collisional processes. They were probably formed by the viscous process in an approximately Maxwellian distribution. I did have time to go into it, and this was an experimental presentation, but quite a while ago we came up with a theoretical process that can lead to a great decrease in the electron temperatures. I don't think I have time to explain it, but it's called the quantum magnetic field effect. Basically, it means that the Landau levels that are quantum mechanically opposed by these extremely strong magnetic fields that we expect to get up into the gigagauss range, make the energy transfer between the electrons and the ions very inefficient, but they do not affect the energy transfer. I'm sorry, I just said that backwards. They make the energy transfer from the ions to the electrons very inefficient, but they don't affect the energy transfer from the electrons to the ions. As a result, you can get an electron temperature that is a factor of 5 below the ion temperature. 25 times below the ion temperature, and a depression of the bremsstrahlung by a factor of 5, which is enough to allow ignition. So that's basically the quantum mechanical effect that we expect if we can obtain these very high magnetic fields.
So the final question, my Edmund.
Both the electrodes, which is right next to the plasma, and the moles of your reactor, or the vacuum mole, will be exposed to gigawatt or the megawatt and alpha radiation. What's the lifetime of the electrodes when the first mole?
Well, we have to separate the research phase, which is what we're in now with a team of 4, from the development phase, which is to turn this into a device that's going to produce commercial fusion, which will have a team of 150 perhaps or 200 and much more money. Obviously, at the moment, our electrodes have been lasting about, our anodes have been lasting about 200 shots. The problem is not at all the alpha particles. The alpha particles are contained by these tremendous magnetic fields in these tiny plasmoids, and they're shot out along with any unburned fuel in this ion beam, which we will actually use to produce most of the energy out of the device. The problem is that even though we're using beryllium, and most of the X-rays will pass straight through the beryllium, the lowest energy X-rays will be absorbed by the tip. So it's actually the X-ray heating that we're most concerned with. The burden on the tip of the anode, which is the hottest place, is about 1 kilowatt per centimeter squared. So it's right at the edge of compressed helium cooling. But it is within the envelope of what people think is possible with good engineering. So it will take a lot of engineering to keep the anode cool. The first ball, which will also be beryllium, will be sufficiently far away because of 1 volt r squared, and the X-rays aren't going to be that significant a problem. So the worst cooling problem is that tip of the anode. But we do make it, but it's manageable. And as I say, it's by X-ray heating, not by particle heating.
Thank you very much.